oscillations in a LC circuit. Now, in this section, we're going to assume that there is no resistance in our circuit. Now, all circuits have a little tiny bit of some resistance somewhere, so this is a simplification. Okay, this is, we do this all the time in physics when we say there's no friction. When, there is a little bit of friction in real life, you just ignore it. Yep. So, but it's very useful. All right, so here's what we're going to do. I am going to put a resistor here at first, and then I'm going to have my famous switch. And then, zoom in. So here I'm going to have a capacitor and an inductor. So this will be C and this will be L. Well, you'll see why here in a second. Okay, so let's say that this is how it is. There's no energy in this circuit, right? There's no current yet, right? There's no current flowing, so there's no energy being delivered by the battery. There's no energy leaving through any resistance. There's no energy stored in electric or magnetic fields in here. But then I'm going to close the switch. Now, what's going to happen at first here is kind of complicated, but if you just think about, let a long time go by in your imagination. Let's just close the switch and let's let a long time go by. What's eventually going to be the current in this circuit? Think. It's got a capacitor in there. It's going to be 0. Right on. Okay. Why is it going to be 0? Because no current, we're going to say the capacitor is not going to fail. And so we will build up charge on this capacitor until the capacitor is full. And so it will eventually build up. Now we're going to do something kind of clever. We're going to take this switch and we're going to instantly close the switch to the other wire, like this. Now when I do that, the resistance and the battery essentially go away. And you're stuck now with an LC circuit. And now let's, in our imagination, think about what's going to happen. I've got energy stored in here, right? In this electric field. But here's what's going to happen. And let's just think of this qualitatively in terms of energy. This capacitor is going to discharge, isn't it? But see, at first, the current was 0. So now it wants to throw all that, get rid of all that current. It wants to just, all that charge. It wants to push that charge out. The inductor says, I don't like it when people change current. Because what does current require me to do in this inductor? It requires me to create a magnetic field, and that takes energy. So I've got energy stored in my capacitor. But then as current starts to flow around like this, I start establishing a magnetic field in here. And the magnetic field will store energy as well. And now I want you to think about this. There's no resistance in this circuit. Now what do resistors do? They remove energy from the circuit and it exits out into the outside world. Well, there is no resistance in here. There's nowhere for the energy to go. So this is going to be equal to the total energy we started with, which was the total energy on the capacitor. At least that's where we're starting this, with all the energy on the capacitor. Well, here's what happens. The capacitor discharges, creates a current. This current creates a magnetic field in here. Now, when the capacitor empties, when the capacitor has lost all of its charge, what happens to the current? Well, it tries to become zero, right? If you're just the capacitor and the capacitor empties out, then you got no more current. But this guy says, no, I don't like it when you try to change current. And so what it does is that it keeps the current going. As the current tries to collapse to zero, the inductor uses its magnetic field to keep the current going. And so what happens is that it keeps the current going, and it fills up the capacitor with positive charge on here. And then you have, of course, that builds up the negative charge on there until the current becomes zero. But when the current becomes zero, there's no more energy stored in the inductor. Now all the energy is stored on the capacitor, but the polarity of the capacitor has reversed. Now all of the charge, positive charge, is on the bottom. But then what happens? The capacitor starts to discharge again, and the whole thing happens in reverse. Now I build up a magnetic field again, okay? And then as that magnetic field tries to collapse, it forces positive charge, and what happens is you oscillate energy between the capacitor and the inductor. Now this is very similar to a pendulum. When I have a pendulum, am I still on screen? Yeah. When I have a pendulum, I have energy oscillating between being stored in the gravity field and being stored in the kinetic energy of the moving pendulum. So the energy just oscillates back and forth. That's what's going to happen here. And what we're going to see is that this oscillation is going to be simple harmonic motion in terms of charge. So let's do this quick. This is going to be Q squared over 2C. Now this is one of the equations we had for energy stored in a capacitor. If you don't believe me, look it up. But I got 3 minutes left and I got to hurry. Plus 1/2 L I squared. Now this is going to be equal to the total energy I started with. In other words, this plus this equals a constant. So then what do? I'm going to take the time derivative of this. Now I'm just going to go through this. Take the time derivative of this. It's not bad. It's just going to be Q over C times dq dt. Plus, and this is going to turn out to be Li di dt. Now, when I take the time derivative of a constant, I get 0. So, now, what is dq dt? It's the current. And I got a current here and I got 0 over here. So what I'm going to do is just divide everything by I, and it cancels out. So I get Q over C plus L di dt is equal to 0. Well, I'm going to solve this for I, or di dt. Di dt is equal to negative 1 over LC times Q. Okay, all of this is algebra, and I'm really trying to rush through this. But what is I? I is it's the second derivative of charge. Folks, This is the equation for simple harmonic motion. When the second derivative is equal to the original function, but opposite in sign, times a constant, that's simple harmonic motion. And omega squared is equal to 1 over LC. Yeah. Okay, we'll review simple harmonic motion and go over this again. This is awesome, you guys. This is, if you graphed the charge on the capacitor as a function of time, if I graphed Q as a function of time, this is the charge on the capacitor, it would look like this. And if I took the derivative of that, that would be the current, and it would be a sine wave. It's awesome. We're out of time, though. We'll go over this again. Bye.